Welcome to The Explainer. I am so incredibly pumped you're here today because we are about to unpack what is arguably one of the most brilliant, volatile, and just flat-out fascinating architectures in the entire history of artificial intelligence. We're going to demystify Generative Adversarial Networks, or GANs. Now, if you've ever found yourself wondering how computers first figured out how to create hyper-realistic human faces totally out of thin air, or how modern AI models can spit out images at those blistering real-time speeds today, well, it all traces back to a high-stakes mathematical mini-max game. Okay, let's dive right in.
To really appreciate the massive breakthrough of GANs, we kind of have to look at the dark ages first. What came before them? You might remember this. Why did early AI-generated images always look like these fuzzy, blurry, indistinct smudges? Well, before 2014, the dominant models were VAEs, variational autoencoders. And their problem was deeply baked into their math. You see, their decoder loss function, specifically the mean squared error, was optimized to just find the mean or the average of plausible images. Think about that for a second. If you take 1,000 different perfectly sharp images of, say, a handwritten number, and you mathematically average them all together, what do you get? Right, a grayish, fuzzy smudge. The math was actively rewarding pixel-by-pixel proximity to a target, not actual visual realism. We desperately needed a completely new way for computers to understand what actually makes an image look real.
And then enter Ian Goodfellow in 2014. He proposed this radical, out-of-the-box solution, Generative Adversarial Networks. Instead of trying to write down some impossibly complex mathematical formula for image density or realness, which, by the way, doesn't actually exist, Goodfellow's absolute genius trick was to just skip density entirely. He decided, what if we force two completely separate neural networks to learn plausibility by competing against each other? It is such a massive paradigm shift. You aren't programming the rules of realism anymore, you're just setting up an arena, throwing them in, and letting the networks fight it out until the fake images become utterly indistinguishable from reality.
Section 1. The Adversarial Game. Counterfeiter versus Detective.
So, we have two players in this high-stakes game. On the left side, we have the generator, which we call G of Z. Think of the generator as our master counterfeiter. Its entire job is to take a random noise vector, which is essentially just a string of pure, meaningless static, and try to mint a convincing fake sample out of it. On the right side, we have the discriminator, D of X. This is our master detective. The detective's job is to look at a sample and output a simple probability score, a 1 if it thinks the image is 100% real, and a 0 if it thinks it's a total fake. It's that simple. The counterfeiter tries to mint perfect fakes, and the detective tries to catch them in the act.
Now, the really crucial part is how these two players actually learn from one another. The training loop is this continuous, alternating dance. Step 1. You train the discriminator by showing it a mix of actual real images and the generator's current batch of fakes. Step 2. You train the generator. And here's the kicker. The learning signal for the generator is based entirely on whatever the discriminator currently thinks makes an image look real. It is literally chasing a moving target. Then, step 3. Repeat. You step one, then the other, back and forth. And you absolutely must feed the generator fresh fakes constantly. If you don't, the math gradients go stale, the learning just freezes up, and the whole system completely falls apart.
But as you can probably guess, a game that sounds this beautifully balanced on paper is an absolute nightmare in practice. This leads to our first massive roadblock, the vanishing gradient problem. Look, if our detective, the discriminator, is just way too good at its job and learns too fast, it becomes completely confident in spotting fakes. And mathematically, when the detective is 100% confident, the gradient, that feedback signal that tells the counterfeiter how to actually improve, drops effectively to 0. The generator goes completely blind, it gets 0 feedback, it can't improve, and boom, the game is over.
So to fix this, Goodfellow introduced this really subtle but incredibly powerful little math tweak, negative log D of G of Z. In the field, this is known as the non-saturating loss fix. See, in the original math, when the detective was super confident a fake was a fake, the equation saturated, and it plateaued to 0. By switching to this non-saturating form, the math basically flips the asymptote. Now, when the discriminator is highly confident, the loss value actually blows up. It gives a massive, super strong learning signal to the generator. It essentially tosses the counterfeiter a lifeline so it can survive and adapt, even when the detective is totally dominating the game for a moment.
Section 2. Why the game breaks. Instability and pitfalls.
Even with that fix, things go wrong. The most famous failure mode of this entire architecture is called mode collapse. Imagine our counterfeiter accidentally draws one specific perfect fake face that completely fools the detective. Instead of learning to draw, other faces, the counterfeiter essentially says, "Awesome!
I'll just memorize that one single trick and mint this exact same face forever. And why wouldn't it? Because the discriminator never flags it as fake, it stops correcting the behavior, the generator ends up producing barely any distinct outputs, completely failing to capture all the rich diversity of the real dataset. It becomes a total one-trick pony.
And honestly, mode collapse is really just the tip of the iceberg here. Training these networks is notoriously fragile. If your discriminator is too strong, like say it hits over 95% accuracy, the generator is dead. You actually have to artificially kneecap the detective sometimes just to keep the game going. Or consider something as incredibly standard as batch normalization. If you run a batch of real images and a batch of fake images through the exact same batch norm layer, their mathematical statistics actually mix together. They leak into one another and completely ruin the training. To run a GAN successfully, you're navigating an absolute minefield of instabilities every single step of the way.
Section 3, the evolution of GANs, an arms race for stability.
Because it was such a minefield, the machine learning community spent years scrambling to tame this architecture. Back in 2015, we got GAN, which introduced convolutions and batch norm to finally create the first truly stable architecture. Then, 217 brought these massive mathematical leaps. WGAN replaced the standard loss with the Wasserstein distance to smooth out those vanishing gradients, and spectral normalization literally constrained the discriminator's weights to further stabilize the game. By 2019, NVIDIA's StyleGAN arrived on the scene, introducing mapping networks that achieved just jaw-dropping state-of-the-art photorealism. And you know what? The innovation hasn't stopped. Even in 2024, models like R3GAN are finding ways to generate massive, high-resolution images without needing all those old mathematical hacks. It has been a continuous, frantic arms race to keep the generator and discriminator in perfect equilibrium.
Section 4. GANs in modern production. The 2026 AI stack.
So all of this begs the question, where does this actually leave us today? We're in an era where massive diffusion models seem to dominate every single headline. Well, GANs might have lost the crown for open-ended, anything-goes image generation. If you have a multimodal task, you absolutely pick diffusion for sure. But for fixed-pose, photoreal human faces, StyleGAN 3 remains the absolute, undisputed, sharpest and smallest king. They are remarkably crisp for narrow domains. And even more crucially, and this is super cool, for fast real-time, one-step text-to-image generation, the industry uses adversarial distillation. We're talking models like SDXL Turbo and SD3 Turbo. That original adversarial trick Goodfellow invented has literally been repurposed today to turn slow diffusion models into lightning-fast generators.
And why is that? Because of the inference advantage. While a standard diffusion model might take 20, 30, even 50 slow steps to generate a single image, a GAN does it in a single blazing fast forward pass. Boom, done. There are no complex prefill or decode stages. There's zero massive memory pressure from a KV cache to worry about. The only state you have to manage is the model weights themselves. And because every single request takes the exact same fixed amount of compute, continuous batching on servers is trivial. Adversarial networks don't just survive in 2026, they thrive because they are absolute speed demons. They are the high-performance engines powering real-time AI everywhere.
Which brings us to our final point, and a thought I really want to leave you with today. As we've seen throughout this explainer, the architecture that started as just two networks fighting over blurry black and white digits has evolved into this incredible, high-speed engine driving real-time image generation. So I really have to ask, as GANs continue to evolve, blending with diffusion and all these other new technologies, will the adversarial game between the counterfeiter and the detective ever truly end? Or are we just going to keep changing the rules of the game? Think about that the next time you see an AI generate a photorealistic face in the literal blink of an eye. Thank you so much for joining me for this explainer, and I'll catch you in the next one.